Hello, my name is Kayla Stan, and I'm a PhD student at the University of Alberta. My research focuses on land cover change and land cover change modeling. This webinar will provide an introduction into the concepts of land cover, land use, and land cover change modeling, with the end of the webinar focusing on model integration. When we look at land use versus land cover, both categorization schemes, it is important to distinguish what each categorization looks like. The four pictures below each show a different type of environment. When we categorize these using land cover, we find that what is on the land surface is described. The first photo shows forest, while the third one shows developed land. Both the second and fourth photos can be categorized as grasslands, despite looking differently. When we, however, look at these photos through a land use lens, though, we can see that the second photo is pasture land, while the fourth one can be considered natural land. When we look back at the forest, it would likely be classified as a natural area, and the developed system would likely be considered urban area or a city. This shows us that the use instead of the cover, so the human attribution of land, is more important when looking at the land use lens. This leads us to the definition of land use and land cover. Land cover is defined as what is on the land surface, while land use refers to the purpose that the land serves. As we saw in the previous slide, grassland could be natural or it could be managed or unmanaged pasture land. When looking at the satellite image, what can we tell? We can see that the area appears to have various green vegetation. There are some straight lines that may be roads, and then there are three perfect circles. What are those? Can we tell what the land is used for just from looking at the image? Or do we need more information? The photo is actually an army base, with those circles being the different potential bomb radiuses, so areas that would need to be cleared. So we can tell from this photo that we need additional information because there is nothing that can tell us what that land use is other than extra information. Now that we have defined both land use and land cover, this brings us to why this topic is important. Humans have been modifying the land surface for hundreds of years, and at a rapidly increasing rate. Before the year 2000, over half of the Earth's surface not covered by ice and water had been modified, and this has increased since. The modification also impacts other Earth systems. These additional changes may be reversible or permanent, but given the uncertainty, it is important to track and understand the historical changes and then predict the potential changes to the land in the future. When we go to the Google Earth engine, this is the time lapse, we can see that the site automatically starts in Miami and shows the growth and development of Miami from 1984 on a yearly basis until 2016. Now, from the original image, we can see some of the growth, but if we zoom out a bit, we can see that the northern portions of Miami have filled in incredibly. Let us move to South America now. So if we scroll over farther, we can see that there is Rhodonia, Brazil. If you click on it, this is slightly different because it doesn't represent urban expansion. This is some of the deforestation that has occurred from the 1980s in the Amazon forest. So you can see the destruction that has occurred in a large tract of land here. So this shows you the power that this sort of tool can use, and it also gives you an idea of the power that land cover change and land cover change modeling can have as we discuss things further. So let us return to the PowerPoint now and see how things progress from here. Now, when we start to look at land cover change, we find that land cover change is not only caused by humans. Natural causes can modify the land surface as well. In this slide, we can see that the top image shows us the changes that have occurred because of a landslide. We see that the before picture is on the left and the after picture is on the right. And in the right, compared to the before picture, we can see that vegetation and urban areas have been destroyed and have been replaced with bare soil in much of these areas. Other natural disasters, including fires, forests, tropical storms, earthquakes, and volcanoes, can also have this type of destructive change. On the flip side of this, natural processes can also repair these changes. Regeneration and succession can lead to the stabilization of an area such as a forest. It will increase the biodiversity, stabilize the soil in the bare ground slopes, and it can protect against flooding. So natural causes can both change land cover towards destruction and towards regeneration. On the human side of this, there are three main drivers that contribute to the alteration of land. The first one is population growth, the second one is agriculture, and the third one is land-based industries. The amount that each of these contribute to land cover change varies depending on your location. Population growth continues to expand cities out, and it puts pressure on nearby areas and nearby land resources. In the rural areas, and in part due to the increasing population needs, farmland continues to be intensive, and it continues to expand into previously natural lands. The third driver of change deals with industry and resource extraction. Open pit mines, oil extraction, and the subsequent disposal of waste can convert large tracts of land from vegetation to bare ground. Or these things can pollute areas or pollute waterways. These three also interact. If, let's say, you have an agricultural land surrounding a city, as the city pushes out into the agricultural land, you still need the same amount of resources, so you then push the farmland out into natural areas. As you develop an open pit mine or an oil reserve, you'll find that you need workers, and so development of cities or towns follow. After these areas are shut down, then oftentimes these cities go to waste but are never converted back to their original form. When we look at impacts this modification of land has, we can look at three different scales, from very local to very global. So the global scale will affect global systems. The regional scales might be a watershed or a province, and the local scales will be in the immediate area. So on a small scale, with population increases and vegetation clearing, problems such as pollution, both air and water, and the stabilization of soil in an area become a concern. This can lead to health problems with air quality or smog, and it can lead to destabilization of slopes, so houses going into rivers as riverbanks change. When we zoom out to look at a large region, such as a watershed or a province, other impacts may start to emerge. After a mass deforestation, the trees that are replanted are often of a common age, and the species are likely the same. This can increase the spread of disease, fire, or pest infestation. An example that we can see of this is the mountain pine beetle. There is often an increased risk of flooding downstream of clearing as well. So this can impact areas further along a watershed. If you start to deforest the headwaters, then more water gets through. There's increased sediment load from the destabilization of slopes and potentially rivers migrating. So this can create hazards downstream. As we increase our scale to global systems, things such as climate can be impacted. If we deforest large areas globally, there is a decreased carbon sequestration potential because of reduced vegetation. This can also have impacts on the ocean carbon content and the feedbacks between the atmosphere and hydrosphere and pedosphere. As more carbon is sequestered into the ocean because of increased carbon load in the atmosphere, this will stay in the water, but as things change and deep waters become surface waters again, This will release large amounts of carbon later on. Additionally, things like increased salinization or increased freshwater load into oceans might become a problem. When we look at the changes in global climate systems, things like the El Nino Southern Oscillation, the resulting changes in the atmosphere can lead to changes in the water. Increased hot water is brought over to the Central and South America coast, and this can lead to problems of the fisheries. So this can show you how land cover change, either on a very small or a very large scale, can have great impacts both locally and globally, from air quality to the collapse of fisheries in some years. When we take a look at the scientific literature, we can also see that other secondary impacts have been found. For example, there is a high correlation between increased population and increased deforestation, especially from the 1980s. We can see from the graph on the left that the increases in population have been very, very well tracked with the increases in deforestation, which we have seen from the slide before, indicating that population growth increases global change or land cover change. The graph on the right shows that there can be secondary effects to this growth. If we take a look at the graph on the right, we can see that there is a population index and there's also a timeline. So the timeline here is from 1970 to 2000, and this is the height of that population growth. And these trends would likely continue if we tracked further into the 2010, 2015, and present. But what we can see is that the population index for all of the species present here shows a decrease, an exponential decrease to be specific. So what we can see is that the marine species, the terrestrial species, and the freshwater species all decrease, with the freshwater species experiencing the highest drop compared to 1970. The terrestrial species show a relatively consistent trend down, but we can see that it increases in its slope from the 1990s. This indicates that it will likely track downwards faster, even though there was a slight delay in seeing its drop. The marine species seem to have leveled out for now, but they go through periods of stabilization from the 1970s. Now that we have gone over both the most common causes and impacts of land cover change, that brings us to how do we measure these changes? During the last 30 to 40 years, we have also seen an increase in the number of monitoring satellites. What are these satellites? So these are satellites that have been equipped with sensors that can look at the land, the air, the water, and the ice, depending on which satellite we're using. And they do this over the whole globe or under specific areas, and they do it at varying resolutions. One of the longest standing satellites that is used for land cover change are the AVHRR and the Landsat systems. And these have been in orbit since 1981 and 1972 respectively. Originally, we saw a monopoly on satellites, predominantly from the United States. But since 2000, we've seen an increase in satellites from Europe, including Sentinels-1 and 2. There's also been an increase in satellites that have been launched from Asia, specifically from China and from India. Now, all of these sensors have varying degrees of resolution, different band lengths, and different projected lifespans. But one of the important things about these satellites is that certain series of satellites have a very, very long time frame. And this is very useful when looking at land cover change. As we can see from the image here, we now have many satellites that we can use, and we have increasing techniques to be able to look at different satellite information in conjunction. There has also been during this time an increase in free satellite images and more open source data. These are useful for tracking things on a global or regional scale predominantly. So to understand the local scale changes, smaller scale instrumentation must be developed and has been developed. On the left, we can see that there are wireless sensor networks. These wireless sensor networks are comprised of small sensors that can be placed in forests, in fields, or anywhere along the ground. The array of sensors then communicate with each other to a single base station, and this is what makes up the network. These are very useful because these networks can detect light and temperature changes within an understory or within a field, and can monitor very small scale changes in the microclimate. This can be especially important along the edges of change or transition zones. So as forest becomes increasingly fragmented, as we saw in the Fredonia case, this information can become quite useful. To monitor larger areas, eddy covariance and weather stations are able to measure dramatic climate changes over time as areas are modified. These information systems can be seen on the right. On the right, we have a monitoring station that includes both information about weather and about the incoming light. In the middle, we have what would be considered a surveyor. Things like a scintillometer can be used in this case, which monitors micro changes in airflow. Eddy covariance is considered one of the golden standards, and if you're interested, there has already been a webinar that describes this more fully. These different systems, though, especially eddy covariance, can also measure things like the carbon potential of an environment. While satellites can be used to look at land cover changes, other instrumentation is useful in providing information about the impacts that these cause on a local level. Those instruments are useful in determining land cover change and also the impacts that are seen from land cover change. As we've seen in earlier slides in this webinar, land use is difficult to determine just by images or by the instrumentation described before. Because land use deals with human attribution of land, additional information is required beyond images from satellites or its impacts. The other information to look for is any other socioeconomic or demographic information. This can include information such as census, population, GDP, industry, or zoning. We can see this on the left and in the middle, where we have a population map and also a zoning map. They provide different sorts of information, but things such as the zoning map can provide a direct description of how the land is intended to be used. Additionally, if there is any information about the biogeographic data in the area, things that include soils, slope, geology, or climate regimes can also be very useful, especially in ruling out some uses. For example, if there is a high slope and poor soil in an area, it is highly unlikely that the use of that area would be farming. While they do not provide necessarily a direct link to what the land use is, they can help narrow down the types of land use that are around. On top of this, if a government happens to hand a land use classification system or maps of land use that have already been done, this can be very useful in determining what the land use change has been over a number of years. It is important to remember, though, that land cover can be described from images from space, but land use, this is highly difficult to do with just that information. This leads us to the question, what can we do with the information? Or how do these images and additional information sources translate into categorization of specific land use or land cover types? There are a number of different methods for classifying information. The first requires the least amount of input and expertise. Unsupervised classification takes the satellite images and groups similar reflectance values together. The reflectance value is what we get off of the satellite image. So it is how we can tell that an image is green. But many satellites also have additional bands, things in the spectrum that we can't see. And so all of these can be then grouped together, and groups of similar type of reflectance would be classified as a single class. A secondary version of that requires slightly more information is called the supervised classification. The supervised classification is similar, but you need ground control points to help create the ranges for each class. A ground control point is an area where you know what the land cover type is. So when this happens, you already have a basis for what a grassland, an urban area, or a forest might be in the reflectance. From there, the points that are most similar to those training points will then be classified as that land cover type. Next, decision trees have many training points, which can be used to train the decision tree or validate the decision tree. What happens is that a number of different trees are created, similar to the supervised classification, but different training points will be used slightly differently in each tree. From there, these points are put through all of the trees, and the class that is most commonly voted for by the trees then becomes what the classification actually is. So this increases the power of the supervised classification by putting multiple different scenarios into effect. From there, these trees or this classification scheme is then validated by putting the validation points through. Now you can change what number of points you put through for training and for validation, but the combined generation of the different classifications is typically better for decision trees and random forests. The most complex of these classification schemes are neural networks. Neural networks require supplementary information and much higher computational power. This deep learning method is becoming increasingly common because of its high accuracy, but is limited by the server power. Each set of images can be used to create a land cover map in a single time step. When this process is completed in the same area over multiple years, this is where the real power comes from. Having these land cover maps in multiple years means that we can compare the extent and pattern of each land cover type. Where land cover differs between years can be used to assess patterns of deforestation or regrowth, areas of urban expansion, glacial movement, or any other surface change. When we have these patterns, that we can then see if there are socioeconomic changes that are also associated, or man-made drivers. We can also determine if the changes are naturally occurring because of natural impacts. We use these associations to tie back to human systems, and this tie can then make information regarding policy more relevant, and it can help us understand the relationships between humans and the environment. This is where we can get the real power of land cover change and time series of land cover maps. Once we understand the relationship between humans and the environment using time series of land cover change, we can then create a further abstraction to project these changes into the future. This abstraction is done by using models. Models provide a representation of real conditions and can be used to create policy interactions or test hypothetical situations and the further response of the environment. You heard an introduction into model specifics in last week's webinar with Jing. And for now, we will briefly touch on models again, and we will look at integration of modeling systems. Models can be first classified into two major types, conceptual and computational. Conceptual models are how we think about the environment or a framework to understand our world. For example, on the right, there are 4 different ways to consider how regional and local drivers contribute to local system response. The first is that each local and regional driver does not interact with any other regional or local variables. One allows within-scale feedback between a driver and other variables. The third allows cross-scale interactions between driving variables. And the last one allows for the interaction between scales in driving variables and supplementary variables. Each of these provides a different way to think about your environmental system. On the other side of this is computational models, which take the conceptual frameworks and represent the interactions with explicit algorithms. These mathematical representations can be simple equations, can be statistics-based, or can have spatial components as well. When we look at land cover models and predicting these models forward, we are talking about computational models. Because land cover has a spatial component attached to it, these models are also spatial in nature. They may be equation-driven or have a statistical basis, or in some cases, much more common today, you can have multiple different types working in a coherent fashion, and these are called hybrid or integrated models. When we start to look at integrated models, what we are required to have are different systems working together. Additionally, we also need different types of information, different variables, and different drivers to help create and validate the models. When looking at this slide, we can see that the shape used to describe the general model setup here is used as a funnel, taking large amounts of information and consolidating it down. When we look at the three circles within the funnel, we can see that there are socioeconomic variables, policy variables, and environmental data. When we look at the environmental data, a number of different types of information can be used. Many of these you've heard about in other webinars. Heat and carbon fluxes, soil, temperature, and structural components of your land can all be used within sensor data. These are often local scale and field measurements. For your land cover, satellites, such as we've talked about, but also drone and other auxiliary information can be used. Finally, ecosystem services, things including biodiversity, are important secondary components when we look at environmental data. All of these can be funneled into environmental data using either spatial or statistical means. Socioeconomic variables we have briefly touched on in the land use section of this webinar. Zoning, GDP, and population growth are some of the most common. You can also have different industry-based variables as well. To create future scenarios, policy information is very important. Both local legislation and international agreements can be very important when looking at future scenarios, as these are often what drives the different land distribution and restriction policies that are put into place. These are the different variables that can be put into models. Now, socioeconomic and policy information can oftentimes be more difficult to include in models because it is often qualitative and not quantitative. Finding relationships between these variables and environmental response can be key when attempting to translate this information from qualitative into a model-based scenario. It is also important to determine beforehand what the purpose of your model is. Depending on the model purpose, the information that you require can be slightly different. If you are not interested in what future policies may hold, then you may not be interested in integrating that information at all. The gray box at the bottom has a number of different optimization or future scenarios, different purposes that your model may be used for. Population growth models, new regulation, or sustainable development are all very human-based and human systems oriented models. These would require more socioeconomic variables and policy information. You may be less interested in what the water or the soil is, or what kind of ecosystem services are there. If you are interested in environmental protection or interested in a future scenario model that deals with pattern-based change, you might be more interested in having all of the sensor data and may require less socioeconomic variables. Given this, it's important, again, to find that purpose from the outset. From there, you can develop a flexible model using the data that you require without having excess noise. It will also help you choose whether or not you want a statistics, spatial, equation, or optimization model. All of these are very powerful in their own right, and understanding what their pros and cons are is very important. Given the complexity of different models and their variability of use, understanding the pros and cons goes beyond the scope of this webinar. Thank you so much for your attention through this introduction to land cover, land use, and land cover change modeling. We hope that you have learned something from this series of webinars, and we appreciate your ongoing feedback. Thank you again, and have a great day.